Okay, so now that you have basically created a parts list for each of those atoms between pages 6 and 10, let's figure out how to put those parts together and actually build these atoms. If you look in the reading section, the web links section of this week's content folder, you're going to see a link called Bohr atom, B-O-H-R. The Bohr was named after Niels Bohr, who was a chemist who kind of came up with a lot of this and looked at the structure of the atom and developed these ideas. And there's different ways to represent these atoms depending on your purposes. We're going to use, for right now, what's often referred to as the Bohr model, B-O-H-R model of the atom. So I encourage you to do that brief reading from that web link. Anyway, we need to talk about how to put these parts together to build a single beryllium atom. And I'll start by saying the protons and the neutrons together sort of conglomerate. They smush together in one sort of centralized location called the nucleus of the atom. I'm going to represent the nucleus as a circle. Now, that's not realistic. Remember, I'm drawing a three-dimensional object on a flat piece of paper here. So right off the bat, this is going to be kind of a cartoonish version of an atom. But it will work. It'll give us the useful information that we need. So I'm going to draw that circle and say that is the nucleus of this atom. In that nucleus exist all 4 protons. So I'm going to say 4 protons. I'm going to represent it with as a P with a superscript plus sign because they're positive. And all 5 neutrons. So there's a 5 and an N with a little 0 because they're neutral. They have 0 charge. So those 9 particles all cram in close to each other in this structure generically known as the nucleus of this beryllium atom. The electrons do not exist in the nucleus. They exist kind of flying around in constant motion around the nucleus. Now I'm moving my marker here as if the pattern is circular, which it is not. But again, because of the limitations of the fact that I'm drawing on a flat piece of paper right here, we have to do something that makes this reasonable. So we're going to say that these electrons exist out here in a cloud, if you will. Some of them exist kind of close to the nucleus. Others exist a little further away. One way to represent that idea is to just draw a circle. Now, the circle that I'm drawing in yellow right now is not a physical structure. It's what we're going to call an electron shell. And this is just really an idea. It's the notion that some of these electrons, some of these 4 electrons, are going to hang around that far from the nucleus. And others are going to be a little further away. So I'm going to draw this second shell. It's almost like if you go to a track and field event and the track has multiple lanes. There's the innermost lane and then the next one out and the next one and the next one. The infield's in here. And they're not all, the runners aren't all in the same lane. So these electrons aren't all in the same shell. They're flying around, they're in constant motion, but they're never going to crash into each other, first of all. And they're not all the same distance from the nucleus. So where are they then? Well, I'm going to use just little green dots. I'm going to use a green pen here and say each dot is an electron, just to make it simple here. You can write little e's with negative signs if you want. I'm just going to draw a dot. So 2 of these 4 electrons that the beryllium atom owns are going to exist in this first shell, and they're going to be a certain short distance from the nucleus. The other 2 are going to be in the second shell, and they're a little further from the nucleus, but again, constantly moving around. Now, a couple of rules that you need to know to go forward and build other atoms. When electrons are placed, or when electrons exist in an atom, only 2 can fit in the first shell. You can't put more than 2 in there. So if you only have 1, you're in business. If you only have 2, you're in business. If you have more than 2, which beryllium does, you're going to have to put some of them in a second shell. Depending on the atom, you may have more than 4. Well, you can house up to 8 in this second shell. So the first shell can hold 2, the second can hold up to 8. If you have an atom so large that you need a third shell, the third shell can hold up to 8. The fourth shell, we're not going to build any that go much beyond that, and the rules start to change as these atoms get bigger. But for purposes of this course, we won't really need to build bigger atoms than that. So we're going to say first shell 2, second shell 8, third shell 8, and we're going to stop there. Yes, larger atoms have more shells than that. But how many electrons you can put in there is something that we don't need to delve into right now. If you take a chemistry class, they'll go into all those rules, and they're important, but not directly relevant to this semester. So we're going to say, here's 2, there's another 2. Okay, so what you see right here is a reasonable, pretty informative representation of a beryllium atom. I know how many protons, how many neutrons, how many electrons. I even know that there's 2 electrons in the first shell and 2 in the second shell. And believe it or not, as you will see within the next week or so of material, it's important to know how many electrons are where, because that's going to help you predict how that atom behaves, and that's really why we're doing all this. We want to know which atoms behave in which way so we can decide whether they're useful to build things like proteins and carbohydrates and stuff that cells use. So being able to draw these and interpret the periodic table is absolutely essential. It's absolutely foundational to moving on with what we can call the biochemistry. You know, what's a protein and how is it made? What's a carbohydrate? What's a lipid? How are they made? How's DNA made? You need to know this stuff before you can do that stuff. So that's why we're spending time doing this. So there's beryllium. I'm going to do a second one with you in this video and then ask you to try some on your own, and we'll compare how you did. We'll take a look after you've had a chance. But let's do this one together. Nitrogen. I'm going to go to the periodic table because I want to know what the parts list is for a nitrogen atom. And I go right here. It's chemical symbol N. It's got a 7 up there. That whole number is the atomic number, so I know it's got an atomic number of 7. The atomic mass is 14.00674 AMU. We're going to round that to 14. If you're wondering why that's valid, why it's okay to take the liberty of rounding that, I will explain that in a future video. But for right now, just trust me, it's okay to round that to the closest whole number, which in this case is 14 AMU. So with that in mind, the atomic mass of a single nitrogen atom is 14 AMU. The atomic number, we just looked it up, it's 7. The number of protons is 7 because they mean the same thing. The number of neutrons, how do you calculate it? This minus that, mass minus number. Well, 14 minus 7 is 7, so there's 7 neutrons. The number of electrons, well, if there's 7 positive protons, you got to have 7 negative electrons to cancel that. So there's 7 of each of the 3 subatomic particles. If I wanted to write that in kind of a shorthand, I could say 14 AMU, atomic number 7. That's a concise way to tell you a few important things about a nitrogen atom. But what I'd like to do down here in this space is actually draw the nitrogen atom. So let's take the parts and put them together in the right way. I've got a nucleus. In that nucleus, I've got 7 protons and 7 neutrons. So 7 protons, again a P with a plus sign. 7 neutrons, an N with a 0 sign. There's my nucleus. I'm going to have some electrons. Specifically, I have 7 electrons that need to have a place to live. So I'm going to have an electron shell that's in close here, the first shell, and it can only hold a maximum of 2 electrons. So I'll put 2 of them in there. The other 5, by default, have to exist in the second shell. Remember, the second shell could hold up to 8. I've only got 5 more to go, so I've got plenty of room. I only need 2 shells. And so I'm going to put 5 electrons here, but watch the way I do this. I'm not just going to go 1, 2, 3, 4, 5 with the dots. I'm going to, in my mind, imagine 4 corners, if you will, to this circle, or like a north, south, east, west. I'm going to imagine that there are 2 places that electrons could exist in this picture here, 2 places here, 2 here, and 2 here. So 2, 4, 6, 8. The reason I'm showing you this is not going to be apparent right now, but by next week's material, it'll be obvious why I'm strongly urging you to draw electrons into their shells in the way that I'm about to do. Don't just go 1, 2, 3, 4, 5 more electrons, I'm done. Instead say, well, 2 could live here, 2 could live here, 2 could live here, 2 could live here. How am I going to fill those slots? I think of having 2 slots here and 2 here and 2 here and 2 here. Here's how I'm going to do it. remember, I've got a total of 5 more electrons that need to go into this shell. I'm going to go 1, 2, 3, 4, 5. In other words, I pair the first 2, then I put one out by itself, and then another one by itself, and then another one by itself. If I had more, then I would start doubling them up. I'd put one here, and then here, and then here. But so in those shells that can hold 8, I put the first 2 together by themselves, and make a little pair there. And then I say, no, you're going to be by yourself, you're going to be by yourself, you're going to be. Instead of going 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, I'm going to go 1, 2, 3, 4, 5. There's a really important reason why I'm very strongly encouraging you to learn to draw them this way, and you're going to see why within the next week of material. Trust me on this one. It's going to be very helpful to you to do it that way. So again, in those shells that could hold 8, in shell 2 and shell 3, pair the first 2, and then put the others by themselves until you have to start pairing them up. So nitrogen is going to look like this. The Bohr model, if you will look like that. It's useful, reasonable to draw. Yes, it's a 2-dimensional drawing of something that's complicated in 3-dimensional, but there's a lot of information packed into that drawing that is really important to know when you want to know what a nitrogen atom does for biology. So what I'm going to ask you to do is move ahead to pages 7, 8, 9, and 10 in the lecture outline. There are more elements with similar empty boxes written there. For each one, you're going to have written the atomic mass, atomic number, etc., and then go ahead and draw out the picture of how those subatomic particles are arranged to form a useful drawing of that atom. Please try all of those. Please ask me if you have any questions. We can discuss that via email. We can discuss it at office hours. Once everybody's had a chance to do that, I'll send you the answers, if you will. I'll send you the what it would look like filled in if you did them correctly, and you can compare what you got to what I send out and say, oh yes, I understand how to do this, or oh, I'm not sure, I should check in and see if I can correct this, because this isn't going to go away. Trust me, knowing this is an important foundation to understanding chemical bonding, which is important to understanding molecules, which is important to understanding cells, and all of biology. So this really is useful stuff to know, and want to make sure everybody's comfortable with it and can interpret the periodic table in this way. So go ahead and try the rest of those pages 7, 8, 9, and top of page 10, and we'll talk more about them coming up.